we got exposed to handbook information in the form of Moody's diagram. Then we asked the question, how do you generate Moody's diagram? So, an example was, you go to a lab and carry out an experiment involving flow through a tube at some fluid speed u, some diameter, some length, which are all convenient from the human perspective. So, in this experiment you may want to change the fluid velocity u and keep measuring the pressure drop P 1 minus P 2. Let us call it, let us give it a symbol delta P. So, the question is, how can this data generated on a lab scale by an individual, how can it be used by somebody else somewhere else at some other point of time? That person may have a different fluid, may have a different diameter. So, this is where principles of similarity become very helpful. We first express the functionality in symbolic form, that delta P will depend on rho and mu, the fluid properties, diameter, length and surface roughness, and of course, velocity. So, this whole thing can be written equal to constant or 0, but let us say 0, assuming constant, a dimensionless constant is absorbed on the left hand side. There could be other factors also, such as let us say temperature, but let us assume that temperature is accounted for through the fluid properties. So, principles of similarity tell you that you can go from the model. This is our model, whatever experiment we have done, in the lab is a model, and you want to transfer this data from model to prototype. This prototype, of course, when the subject was being developed, prototype was larger than the model, but now there is no such conditionality. Prototype may be much smaller or much larger than the model. So, to carry out this mapping or transformation, we express the relationship in dimensionless form. So, a useful result in this context is the Buckingham pi theorem, which tells you that if you have n variables, in this case 1, 2, 3, 4, 5, 6, 7, in m dimensions, which is mass, length and time, then you will have n minus m, which is 4 dimensionless quantities, and these are these dimensionless quantities. Well, Buckingham in his original paper used the symbol pi. So, we continue to use pi. These are called pi parameters. So, that means you will now have a new relationship pi 1, pi 2, pi 3, pi 4. It is a new relationship. So, this is a reduced form. So, this reduced form in dimensionless parameters can be used for the prototype. Okay, so, continuing with this example, to find the pi parameters, we first identify a basis, and as some of you correctly pointed out, there is no unique way of establishing the basis. So, as we go deeper into the subject, your awareness will increase further, and then the choice of the basis variables will become sort of self evident. So, right now it may seem as if I am telling you what the basis should be, later it will be clear to you. I mean, on your own you would choose the same basis. But the result, the choice of these pi parameters indeed depends on what your basis is. So, this basis you will have m of this is the original dimensionless set delta p rho mu d l epsilon and u. From here you pick m variables as basis in such a way that all the dimensions involved in the discussion are covered. So, last time I picked rho u d. So, I will write here for example rho u d. Then pi 1 can be written as rho to the power a 1, u to the power b 1, d to the power c 1, and then here you pick one of the variables that is left out, let us say L. Pi 2 will be rho to the power a 2 u b 2 d c 2, and let us say epsilon. Pi 3 will be the same thing, and you put mu, and pi 4 will be the same thing, rho raised to a 3, u raised to b 3, d raised to c 3 delta p. Then insisting that pi is dimensionless, the pi variables are dimensionless, and substituting, let us say rho will have dimensions of mass per unit volume, velocity will be distance or length, this is distance per unit time, and d will be just L. I think there is some mix up between the length L here and this length here. So, make sure you keep them distinct. So, when you substitute, you will get quite readily, see this L does not have mass. So, this A 1 will be 0, B 1 will be 0, and C 1 will turn out to be minus 1. So, pi 1 will turn out to be L over d, which clearly is dimensionless. So, completing these calculations, pi 1 will be L over d, pi 2 is equal to epsilon over d, pi 3 will be mu over rho u d. Now, you recall from your Moody's chart that rho u d over mu, what is it? Reynolds number. Do not say Renault, it is Reynolds. The name is so important for us, we have to pronounce it properly. Reynolds number. So, if pi 3 is a dimensionless quantity, 1 over pi 3 is also dimensionless. So, we may as well choose to work with rho u d over mu. And pi 4 is delta p over rho u square. So, complete the calculations, leaving it to you. Of though epsilon will have either I think some table was given to you. You remember the tutorial problem sheet, epsilon has been given to you. I think that because it is an American book, it also has feet, inches, meters, millimeters, microns. So, units of length. And what is epsilon? So, epsilon is an average height of the roughness element. So, this roughness is distributed over the surface and its typical value, not maximum or minimum, but something like a representative value. So, one such statistical measure which is commonly used is, what is this commonly used statistical measure for a variable that is sort of randomly distributed? RMS value, RMS with respect to the average value, with respect to the mean. Okay, so, the functionality, that means, I have carried out some experiments, I have tabulated the data and now I retabulate the data in terms of pi variables as equal to 0. Let us call this f1, or you could write delta p over rho u square is some function of rho u d over mu, which is in our terminology it is Reynolds number. Epsilon over d, L over d is equal to delta p over rho u square. Okay. Now, with reference to our energy equation, you know that delta p over rho is pressure head, u square over 2 is the kinetic head, and g z is the gravitational head. Is it not? All three together will represent the mechanical energy of the fluid at some location. If you want total energy, what do? You have to add internal energy to it. So, because of that u square over 2 in the energy equation, it is quite conventional to replace rho u square by half rho u square. So, just because any time you say u square, we really use half rho u square. So, the half u square. So, it is quite conventional to put a factor half along with it. It does not change the dimensionless relationship. It is still, see, the functionality itself is not specified. It just says it is a function, that is all. And that functionality has to come from, in the context of handbooks, it has to come from your experiments. So, you have a tabulation of this data. Then what does the principles of similarity, what do they tell you? They tell you that if L over D model is equal to L over D prototype, epsilon over D model is equal to epsilon over D prototype. So, in the language of principles of similarity, this is called geometric similarity. So, if the principle of geometric similarity is fulfilled, and rho u d over mu model is equal to rho u d over mu prototype. So, it is not so clear, but as we go along it will become it will be revealed that indeed it is an expression for dynamic similarity. What is dynamic similarity? It tells you that the relative importance of forces going from the model to the prototype should be preserved. So, what are the forces here in Reynolds number? We have not done it, but you may think of rho as being associated with mass and therefore, inertia, and mu with viscosity and therefore, viscous forces. So, it is a ratio of inertia to viscous. So, that is a tentative explanation. So, it is a principle of dynamic similarity. So, if the principle of geometric similarity is fulfilled, if the principle of dynamic similarity is fulfilled, then all principles of similarity are fulfilled and you can map data from the model to the prototype. That means, the conclusion is delta p over rho u square for the model is equal to delta p over rho u square for the prototype. So, this dimensionless data, that column that you have for delta p over rho u square can be used for the prototype. Now, this relationship, this is still not in the form of Moody's diagram, but you may recall from our momentum equation and energy equation. We had done these calculations for flow through a tube. The geometry is flow through a tube. Okay. So, if you recall, we said delta p balanced viscous forces and there was a proportionality with respect to length. The pressure drop linearly increased with the length of the tube. If you remember the application of momentum equation, okay, you remember the application of momentum equation for flow through a tube. Okay. The momentum fluxes going in and coming out, they cancelled each other. So, when you did a free body diagram of the fluid contained in the tube, you got this result that delta p scaled with the length of the tube. So, if delta p over rho u square is going to have linearity with respect to L over D, then you can take it out times F3 you can write it in this form. So, it is delta p over half rho u square is proportional to L over D. Okay. If all other quantities are constant, then it is proportional to L over D. So, you can take it to the left. So, let us write it as and what is the quantity on the left? What is the quantity on the left? Friction factor F, right. So, that is lowercase f. There are too many functions here. So, which is an expression of Moody's diagram. So, if you asked why is Moody's diagram plotted in that particular way, the explanation is it takes data in dimensional form, casts it in a non-dimensional form, so that you can go from a model to a prototype. So, let us okay. So, that is why we have Moody's diagram. So, this approach does not tell you why the function has that particular shape. We are still in the domain of global analysis. It is only by looking at the flow field in detail will you be able to explain why. You can always ask, why is there no dependence of this left branch on epsilon? You can ask, why is there a jump here? You can ask, why does this curve tend to become flat with increasing epsilon over d? So, these questions cannot be answered in the global framework. For that, you have to go into a local analysis, a local description of the flow field. So, this global versus local. So, we have done global analysis, whatever can be done just by applying the principles of mass, momentum, energy on a global scale. But if you want to explain the trends contained in the data, you have to look at the flow field in detail. That is local analysis. So, rather than work with a control volume, we will start going towards a small fluid element in the continuum domain, of course, but from a large volume to a small element. We will start making this transition on Wednesday, okay. And then try to seek explanations for why the graph looks like this. Right now, this is the data, and we can use it for our calculations. Now, second, you can ask, can it be used? So, this data, let us say I did experiments in water, can it be used in air? Yes, because rho and mu are general purpose variables that have been factored in the original relationship. Yes, can be used in air. Can I use it in let us say salt solution or sea water? Yes. Can it be used for oil? Yes. So, though the data was generated with let us say distilled water, you can use it for salt water, air, oil, but let us not get carried away. What about blood? So, does see we had these two flow these two fluid properties in our discussion. One is density. Does blood have well defined density? It's either yes or no. No. Why? Yeah, you can think of blood as a particulate fluid, okay, with RBCs traveling with plasma in the background, but the number of RBCs is quite large. So, on a large scale probably there is a well defined density, on a small scale you do not have a well defined density, because you have particles as well as a liquid. It's like a slurry, a particulate mixture. It's like dust particles flowing with water. Does it have a well defined viscosity? So, where does viscosity come from? It comes from our Newton's parallel plate experiment. So, in Newton's parallel plate experiment, f over a plotted as a function of u over h was a line, and the slope changed with the choice of the fluid contained between the parallel plates. The slope was then given the symbol viscosity. And we also commented that not all fluids will display this behavior, but a very vast majority of them, like air, water, oils, salt solution, they indeed display linearity between f over a and u over h. And there is a unique viscosity for each fluid. But if you plot this curve for blood, it has some shape. There is a straight line for small values of u over h, but tends to flatten for larger values of u over h. So, it does not have a unique viscosity. Okay. So, it has some viscosity for small values of u over h, and it has in fact, a smaller viscosity for larger values of u over h. So, this is blood. So, such fluids are called non-Newtonian. They do not have a well defined viscosity. Viscosity indeed depends on that u over h variable. So, if it does not have a well defined viscosity, then of course, it has what it has is a collection of viscosities. So, let us say it has two viscosities, mu 1 and mu 2. Then you have to put mu 1 mu 2 in the functional relationship, not just a single mu. Okay, so, blood is non-Newtonian, and Moody's chart will hold only for Newtonian fluids. For which there is a clear definition of viscosity. Okay, so, that is how the data generated on a lab scale is used for, let us say, finding the pumping effort for drawing water from a well or power output of a turbine. In all those problems, we use the same Moody's diagram, because as long as we match the Reynolds number and the surface roughness, we can get the friction factor. Let us look at another example of this is external flow. This is flow over a circular cylinder. Given by a diameter d and length L. L is normal to the plane of the blackboard. When you have internal flow, then you start looking at pressure drop. When you have flow over an object, you start looking at the force acting on the object. Now, force acting on the object in the flow direction is called drag, right, and we discussed some methods of measurement of drag. Do you remember any one method of measurement of drag? There was that wake deficit method, where you map the velocity field downstream of the object and do a control volume analysis to find the force acting on the object. So, using some method now, if it is flow inside a tube, you could probably work with water. You can also work with air. Those could be your working fluids, but if it is external flow, then air is more convenient to handle compared to water, though of course, you can use water also. So, if you have flow of air, that gadget is often called a wind tunnel. So, if you go around the campus, you may see a wind tunnel, large wind tunnels. Okay. But sustaining water flow over such large cross sections is difficult, but we also have water tunnels. You can have wind tunnel for air, you can have a water tunnel for water, you can have oil tunnels for oil. So, what is the purpose of all these devices? It is to create this flow field. This flow field is created in a wind tunnel for air. So, if I tell you in a wind tunnel experiment, do not ask me what is the working fluid. Is it air, water? What will it be? It is air. Okay. So, in this experiment, so let us write the force acting on the object in the flow direction is drag. Force acting on the object normal to the flow direction is called lift. Okay. Now, this object will also experience a moment, okay, sometimes called, if it is a moment whose axis is normal to the plane of the blackboard or this whiteboard, it is called pitching moment. So, this d is a function of course of u, it is a function of fluid properties, it is a function of d and L. It may be a function of epsilon also, just to change the problem from what we had in a tube. Let me drop epsilon. So, let us assume that the surface is smooth. What does it mean? It means epsilon is 0. So, this function is equal to 0. Okay. So, you go to a wind tunnel, put a cylinder in it, measure data, collect data for various values of u. Okay. Now, you say I have this database in dimensional form and I want to give it to somebody else who has his own velocity, his own fluid, who has his own diameter. I worked with a wooden cylinder, he is going to work with a let us say a mild steel cylinder. So, you can be confident because you may rely on the well proven principles of similarity. So, before you transfer data from you to your friend, reduce it to dimensionless form, unless if he is your enemy, give it to him in dimensional form. So, friend, give it in dimensionless form. So, you can re-express D as f 1 D is equal to f 1 u rho mu over L, and n is equal to 1, 2, 3, 4, 5, 6, m is equal to 3. Let us choose rho u d as a basis. There is no mystery behind it. This rho u d will generate Reynolds number very comfortably. Okay. So, what are the units? Okay, now you have to be careful about delta p had units of Newton per meter square, right, which is what? Kg meter per second square meter square, which is kg meter kg per meter. What is happening? Newton is where is my mistake? It is correct. So, that will be kg per meter second square. Yeah, that is all right. Yeah. So, drag will be in units of newtons, which you have to reduce to dimensions of mass, length and time. So, Newton is mass times acceleration, right. So, you have to substitute dimensions appropriately. So, pi 1 let us say it is L over d, pi 2 will be rho u d over mu, and pi 3 will be so it will take some time to calculate pi 3. For delta p it was rho u square, and this is not Newton per meter square, it is newtons. So, it will be you will have that d square factor, square of a linear dimension. So, rho u square we substitute as half rho u square is equal to some function of rho u d over mu and L over d. So, this cylinder is kept normal to the plane of this blackboard. If the flow is uniform in that direction, then if you double the length, the force also will double. So, once again you have a linear dependence between force acting on the object and the length of the cylinder. So, extracting L over D to the left hand side, you have d over half rho u square into L d is equal to function of Reynolds number. So, this product of L and D, see this is D and times L. You can imagine that L times D is the projected area of the cylinder with respect to the flow direction. Okay. So, this L times D is given a symbol A P, projected area. And the left hand side, like friction factor, is given a symbol C D, capital C suffix D. It is called the drag coefficient, C for coefficient, it is called drag coefficient. If it is lift, then it will become lift coefficient. Okay, so, you have generated that data, reduce it to this form. So, C D is only a function of R E. So, for a circular cylinder, the force acting on it depends only on, in dimensionless form, depends only on Reynolds number. Of course, it will depend on surface roughness, but we have assumed a smooth surface, depends only on R E. So, C D is a function of R E. Now, if you do a similar analysis for a sphere, then projected area is what is the projected area? It is just pi d square, right. So, the relationship is expressed as drag divided by half rho u square times projected area, that is a function of Reynolds number. It will be a different function compared to a circular cylinder. Now, this graph has some shape like this. Some 10 raised to 5. Now, the sphere also has a very similar variation, but the numbers are different. So, this graph has its own peculiarities. There is no jump, but you can see the initial part goes down, that is Reynolds number increases, drag coefficient decreases. What happens to drag itself? Reynolds number is proportional to velocity, but drag coefficient has u square in it. So, as velocity increases, if you look at drag itself, it also increases linearly, because drag coefficient decreases as 1 over u. So, when C D becomes constant, drag is proportional to velocity square. So, this dashed line, so this drag is proportional to u. For higher velocities, drag is proportional to u square. So, this is the data for a circular cylinder. So, the functionality changes with fluid velocity, and if you look at this intermediate region, drag coefficient is nearly constant. Okay. And this constant value is around some 1.2 to 1.4. Beyond a certain Reynolds number, you see a sudden dip, and it comes down to about 0.4. Okay, so, there is a jump here. Now, when you do an experiment, you will see all these things happening, all these variations, but you cannot explain from a global perspective. So, this we will be looking at flow behavior in greater detail from Wednesday, so that we can explain this particular shape of the graph. Have you seen this graph earlier? No, I sent it to you. This you remember, this also you remember, but here it is. There are two graphs, the one above is for a circular cylinder, the one below is for a sphere. Make sure you have this data with you. Okay, if not, tell me, then I will send again. Those circles are all experimental values. So, you can see there is an initial part, there is an initial reduction, then near constancy, and then there is a big jump from about 1 to about 0.4. Okay. And then again slowly it increases, and this Reynolds number range, here it is from 0.1 to 10 raised to 6. So, very wide range. Anyway, he also uses the definition V d over nu, that nu is mu over rho. Okay. So, we use rho u d over mu. Something similar happens in the case of a sphere also. Okay. So, this graph should be available. This is handbook information. Okay. Now, so, what do you do with data of this form? You can do all kinds of calculations, but let us do a particle trajectory problem. Let us start with a simple situation. This is a column of oil and you introduce a spherical particle which starts to move under its own weight. Small particle starts to move under its own weight, and you want to find out how it is going to accelerate, what essentially is its movement in that column of liquid. So, viewed from the perspective of the particle, that is something you have to realize, that this graph C D versus R E, in the lab you may carry out the experiment with a fixed cylinder and there is air going past the cylinder, but you can also use it in a let us say stationary medium with the particle moving, the two are equivalent. So, if the particle is in movement, is in motion, then let us say u p is the particle velocity. Then m times the acceleration of the particle will be equal to. So, let us work with a coordinate system which is positive in the downward direction, minus rho fluid g times volume minus. So, this particle will experience force on it, that is what the handbook information tells you. There is a drag acting on the particle given by the drag coefficient C d, which is a function of R e times half rho u square, which is u p square, times A p, with an initial condition okay. So, you started with your time is up. So, we will quickly wrap up this problem next time. Okay. As an example of handbook data for drag coefficient acting on a cylinder or a sphere. I think here a particle is a sphere.